All right, welcome. If you've got a quiz coming up on the first 7 sessions of Applied Business Analytics, you've definitely come to the right place. We're going to do a quick, high-speed review of all the core concepts to get you totally prepared. So let's just dive right in. Okay, so here's our game plan. We're going to hit 5 key areas. First, the 2 main ways machines actually make predictions. Then, we'll look at the logical flowchart of decision trees. And after that, the totally different approach of the probability machine. Then we'll meet the common enemy of all models, a little villain called overfitting. And finally, we'll talk about the big choice you have to make as an analyst.
So first things first, the whole goal here is to get a machine to make smart predictions, right? Well, it turns out there are 2 completely different ways of thinking about how to do that. You can think of them as 2 different core philosophies.
I mean, think about it for a second. Every single time your inbox catches a spam email, that's not magic. It's a model, somewhere making an educated bet based on all the data it's seen before. The real question for us is, how does it make that bet? What's the strategy behind the scenes?
And that brings us to our 2 main players. In one corner, you've got a method that thinks like a detective, following this super logical flowchart of yes or no questions. We call that a decision tree. And in the other corner, you have a method that thinks more like a casino, constantly calculating probabilities and just playing the odds. That's naive Bayes. 2 totally different mindsets for solving the same problem.
Let's start with the detective, the decision tree. Honestly, the best way to picture this is like a high-stakes game of Guess Who, but for data. The model is just trying to ask the most revealing questions it can think of to narrow down the answer as quickly as possible.
Now, the technical term for this whole process is recursive partitioning, which sounds fancy, but it just means splitting the data over and over and over again. You start with this one giant, messy pile of data, and the algorithm's entire job is to find the best questions to split it into smaller and, more importantly, pure piles.
And that word purity is crucial. The algorithm is obsessed with it. A group is 100% pure if every single person in it has the same outcome. Like, say, every single person in that little group defaulted on their loan. The tree is always searching for that one question that will split the data into the purest possible groups it can create.
What's really cool is that even within this one idea of decision trees, you've got different styles. Think of it like a sculptor versus a gardener. The sculptor, which is an algorithm called CART, starts with this giant block of data, carves a massive, super detailed tree, and then carefully chips away the parts that aren't actually useful. But the gardener, Chide, is way more careful. It only adds a new branch if there's really strong statistical evidence that it's a good idea.
And what's really interesting here is the trade-off this reveals. CART, our sculptor, with its deep, complex trees made of simple yes or no questions, is an absolute beast when it comes to raw predictive accuracy. But Chade, our gardener, builds these wider, simpler trees that are amazing for interpretation. For actually explaining to a manager why a certain decision is being made.
Okay, let's switch gears to our second philosophy. This one is fascinating because it's a model that operates on an assumption we know is completely wrong, and yet somehow it works incredibly well. Let's meet naive Bayes.
Now, this model is called naive for a really good reason. It makes one gigantic, simplifying assumption that every single piece of information is totally unrelated to every other piece. So for a spam filter, that means it assumes the word free has absolutely no connection to the word money. Now, we know that's not true, but this exact assumption is what makes the model so lightning fast and surprisingly powerful.
This is the perfect way to think about it. The algorithm doesn't care one bit about grammar, sentence structure, or context. To naive Bayes, the phrases deal of a lifetime and lifetime of a deal are exactly the same thing. All it cares about is which words are in the bag.
So this whole bag of words thing is actually shockingly effective, but it has one huge, potentially fatal weakness. What happens if a word pops up in a new email that the model has never, ever seen during its training? Well, this leads to something called the zero frequency problem.
And this is an absolute showstopper. If the word webinar, say, shows up in a new email, but that word was never in a spam email in the training data, its spam probability is 0. And because the final calculation multiplies all the word probabilities together, the entire equation gets wiped out by that 0. The model completely breaks, and it wrongly concludes there's a 0% chance the email is spam.
Fortunately, the solution is just incredibly elegant. It's called Laplace smoothing, and what you do is you basically give every possible word a tiny head start. You just add 1 to all the word counts, pretending you've seen every word one more time than you actually have. And just like that, no probability can ever be zero. Problem solved.
Okay, so here's where the stories of our logical detective and our probability casino start to come together. It turns out both of these powerful but very different approaches face the exact same enemy, a villain that we call overfitting.
The central battle in all of predictive modeling really comes down to finding that sweet spot. It's the classic Goldilocks problem, right? You don't want a model that's too simple, you don't want one that's too complex, you need one that is just right.
So on one end of the spectrum, you have underfitting. This is a model that's way too simple. It just hasn't learned enough from the data. It's kind of like trying to predict the weather by just saying, it'll probably be the same as yesterday. You're completely missing the real patterns. But on the other end is our main villain, overfitting. This model is way too complex. It's like a student who memorizes the answers to the practice quiz perfectly, but then completely bombs the final exam because they never actually learn the concepts. The model memorizes the training data, all the noise and randomness included, so it just falls apart when it sees new, real-world data.
And this brings us to the bias-variance trade-off, and this is a really key concept for your quiz. Bias is the error you get from being too simple. That's underfitting. Variance is the error you get from being too sensitive and complex. That's overfitting. And the really tricky part is, when you try to push down on one, the other one inevitably goes up. Your whole job is to find that perfect balance point in the middle.
So how do we fight this villain? Well, we've got two main weapons in our arsenal. First is parameter tuning, where we basically set guardrails for our model. We might tell a decision tree, hey, don't you dare get any deeper than 10 levels. But our absolute best weapon is something called cross-validation. This is the ultimate reality check that gives us an honest, reliable score of how our model is really going to perform out in the wild.
And that brings us right to the final and maybe the most crucial decision an analyst has to make. This isn't just about which algorithm is better on paper, it's about a fundamental conflict between two very different goals.
So the whole thing boils down to this. What is your number one objective? If you need the absolute highest accuracy possible, and you honestly don't care how the model works, like in an automated fraud detection system, you go with a powerhouse like Hart. But if you need to explain the results to your boss and understand why customers are behaving a certain way, you absolutely need an interpretable model like Chade. The business goal always dictates the right tool.
We'll finish with this one thought to keep in mind as you prep for the quiz. The fact that a model like Naive Bayes, which is built on a wrong assumption, can be so incredibly useful. Well, that tells us something important. It tells us that understanding these trade-offs, like accuracy versus interpretability or bias versus variance, is way more important than just memorizing formulas. That's the real key to applying business analytics in the real world. You're ready. Good luck.